Okay, Sweetwater River Bridge, 1929, made up of 2 trusses. Now, what kind of truss is this? Parker truss. One truss on each side. More trusses joined at the top. So a plane truss is a system of bars in a 2-dimensional plane and joined together at their ends, thereby forming a framework. So you have a truss on each side here. Well, a simple truss would just be a framework of triangular units. We assume the members are connected at their nodes with frictionless pins. And we're assuming axial forces only, so no loads applied mid-span. Mid-span meaning between the nodes. So this bridge is in Spring Valley, California. This is Spring Canyon. What kind of truss is this? Can I get closer? Alright, how's this? So this looks to be a pedestrian bridge across the canyon. Okay, so I'm going to walk across the bridge. Looks like it's made of 2 trusses. A truss on each side. This bridge was made for pedestrians only, obviously. Now when I get to the other side, this is an old railroad right-of-way. The trains are long gone, but the right-of-way is still here. I'll look down. Oops, sorry, I think my finger got in the way. And then the other side. Okay, so I crossed the bridge. And, this is the old railroad right-of-way. Trains don't run here anymore. And looking in the other direction, the trains used to go around this curve. Okay. You see the truss members here? So this looks to be a trapped truss. Okay, let's cross back to the other side. So I've got 2 trapped trusses. crossing the canyon. Maybe I can get a better view if I go up this hiking trail. I can get a view of the other side of the bridge. Okay, so this is the Truss on the other side of the bridge. What's your favorite mode of conveyance? You like walking, driving your own personal car, riding the bus, riding a light rail vehicle, riding a train? Well, we often use trusses in bridge design. So this was a pedestrian truss that I just showed you. And then we can see over there on the other side the old railroad right away. The trains are long gone though. Okay, determinacy of a truss. Okay, if a truss is determinate, I can find all the external reactions, I can find all the bar forces. Okay, so let's say that B is the number of bars or number of members, R number of external reactions, N number of joints. So if B plus R is equal to 2N, then it's a determinate truss, statically determinate. If B plus R is greater than 2N, it would be statically indeterminate. If B plus R is less than 2N, then it's unstable. Now, going back to being indeterminate, if it is indeterminate, then the degree of indeterminacy is B plus R minus 2N. So that's what you see at the bottom there. Now be careful with these conditions. The first condition and the second condition, determinate and indeterminate, those are necessary, but not sufficient for stability. So I know that if B plus R is less than 2N, then it's unstable. Being determinate or indeterminate, these are necessary for stability, but not sufficient for stability. So if it's stable, it will fulfill one of these two. But just because one of these two inequalities is satisfied, that doesn't necessarily mean that it's stable. For example, we have here a bowstring truss. Okay, so look at how I label the nodes here. So I want to know about the degree of indeterminacy, or maybe it's determinate, I don't know, or maybe it's unstable. Why don't I count the number of bars, number of external reactions, and the number of joints? So I throw some reactions on there, A sub x, A sub y, G sub y, and I threw some loads on there, 2 kilonewtons vertically at C, and then at node F I've got 1 kilonewton acting to the left. Okay, so how many external reactions are there? 3. So R is 3. B is 19, the number of bars. There are 19 members to this truss. And then N is 11, the number of joints, A through K. Okay, so if you calculate B plus R, that'll be 22. 19 plus 3 is 22. And then a 2N, 2 times 11 is 22. So as I said earlier, if B plus R is 2N, then it's determinate. Is it stable? Okay, so B plus R is equal to 2N. That's necessary, but not sufficient for stability. So even though I fulfill that equation, the requirements of that equation, that doesn't necessarily mean that it's stable. So stability is something that you can kind of tell by inspection. Can you imagine this moving, assuming that the equations of equilibrium are satisfied? Is there any way that this could easily collapse? It looks fairly stable. It does look stable. So I would consider this a stable truss. So this is called a mono truss, oftentimes used for a roof structure. So what about the determinacy or indeterminacy of this? So what am I counting anyway? The number of bars. How many bars are there? How many external reactions? How many joints? So let me count all those up. Okay, so for this mono truss, I threw some reactions on there. 2 at A, 1 at B. I didn't label every joint, but I did label A and B, the left and the right supports. So how many bars do I have? 1, 2, 3, 4, 5, 6, 7, 8, top and bottom. 9, 10, 11, 12, 13, 14, 15. So 15 bars, number of reactions 3, 2 at A and 1 at B. Number of joints 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 joints. So B plus R, that's 18. And 2 times N is 18. It is a determinate mono truss. I can tell by inspection that it's stable as well.